Okay, so let's start. So our next speaker is D. Yogeshwaran, who's a professor at ISI in Bengaluru. And he works on various topics in probability, including random geometry and random topology, etc. And today we'll be talking about continuum percolations.
Thanks, Piyush, and thanks to Akash and Anand for inviting me. Happy to be here again and speaking. So this is a joint work. First things, the talk slides are already available both on the website of the event as well as you can find it on my website. And this is a joint work with Giovanni and Gunter, which started just before COVID in a conference, ended up meeting and discussing, and then continued with Chinmay later. Before starting out, it's something that, I don't know, like I've heavily been motivated by questions. The work has borrowed heavily from computer science literature. And a lot of my work, I've been an audience in computer science talks and enjoyed it, but I don't know how well I'll be to speaking to in a computer science audience more maybe. So please, if there's anything, please interrupt. Please feel free to ask. It's a kind of new thing to talk to a computer science meeting for me. And okay, so as an outset, I'll say there was a kind of thing that was due to Jean Bourgain that functions of high complexity can be studied via their Fourier spectrum. And then there are various surveys on this kind of philosophy of various natures. In particular, the one I'll be heavily relying upon is the one that inspired our work a lot is the one by Christophe Garba on Oded-Stram's contribution and work of Oded-Stram itself. But as you can see, there were Friedgut, who was here last week, he wrote, in fact, it was only during his talk I found this survey on various problems where he has benefited from KKL, is the Kahn-Kala lineal, who are one of the first people to use Fourier analysis in the study of Boolean functions and triggered a lot. Okay, so not directly related, I will introduce all the key objects in Fourier analysis of Boolean functions. And I will move to continuum and discuss the analogs in continuum. I won't say any results on Fourier analysis, but it will be an exercise to guess the results based on the continuum results I present. Okay, so I won't say the discrete results, but I'll present the continuum ones and you can guess what would be the discrete analog. Okay, what are the key things? So first is I take a function of n bits. Okay, bits for me is plus minus 1. And a function also takes value in plus minus 1. Okay, and I'll assume the bits are, for simplicity, IID symmetric bits. Okay, taking plus and minus 1 with probability half each. And then you want to write out a series or expansion for such functions. And the basic functions are what are called characters or characteristic functions. It's just to take any subset of n and multiply the bits. Okay. So you just multiply the bits in any subset of n, and these are what we call as characters. And if it's empty, that is just one constant function. Basic, what's called Fourier Walsh expansion, something that underpins all of this, is that I can write out any function of this form as a sum of some constant times these characters. And the constant has an explicit inner product structure. Okay, the inner product here is given by the expectation with respect to the IID symmetric bits. So it's expectation of f with chi. Okay, so this is exactly like in what you have seen in various forms of Fourier analysis. So any function can be written. So there are 2 to the n many elements. It's a sum over 2 to the n many elements. Okay, so you can write a function. What is hidden here? Chi s under this inner product form an orthonormal basis. The way to show this is you can try to show that chi s forms an orthonormal basis under this inner product. And a few quantities which are very useful in studying this. First thing is what is called the Fourier energy, is you look at all sets of cardinality k and you sum up the square of the Fourier transform. Okay, the square of the frequency of level k. Okay, this is the total frequency at level k. It's called the Fourier energy. And just by Planck-Errels, the total sum has to be 1 because my function takes values plus minus 1. That's one reason for taking the function to be plus minus 1, because the square is always 1. Okay, So by Planck-Erels, the sum is equal to 1. And spectral sample, which is one of the key concepts which drives this business in some way, is that you define a random subset of n. Okay, its n is 1 to n. I take a random subset with this probability. The probability it takes any fixed subset is f hat square. Okay, is the square of the frequency of that set. This is what is the way the random subset is chosen. And what is the probability the random subset has cardinality k? Just by definition, it's nothing but the Fourier energy at k. So I take a subset of cardinality k, okay, by the Fourier energy at k. I choose a cardinality of a subset based on Fourier energy. And then after that, I sample among all possible k subsets. I sample proportionately based on the individual Fourier spectrums. Okay. So this is the idea of spectral sample, is to somehow use the spectrum of the function to come up with some random subsets. Okay, you choose a random subset which is in some way encodes the spectrum, and a very, very crucial thing that is going to be helpful later, you will keep seeing analogs of this in various guises. Suppose I start with these bits. I have n IID bits. I decide to resample each of them with a probability 1 minus e to the minus t. That is, I first toss a coin whose heads probability is 1 minus e to the minus t. If it is heads, I resample a new symmetric bit at that position. If not, I keep the same bit. Okay? So I get an epsilon t, which is now the resampled bit. Epsilon is the original sequence of bits. It's the new resample. One big advantage of this kind of expansion and orthonormality property is that I can write expectation of this product. Turns out to be, it's nothing but some Laplace transform of the cardinality of the spectral sample, and even further a simple expansion tells you it has a neat product structure in terms of k and the energy. Okay, what I would like to highlight is this structure. Now this entirely drives this kind of view from what Bourgain's, that if I want to know is something sensitive to, I want to know as a function of t, does f of epsilon t differ from f of epsilon? I want to know how sensitive is it as a function of t. It's very useful to understand this product form, product expectation or covariance. Okay, this is what will come in the covariance. And then it is important to understand that it is sensitive if the Fourier spectrum is concentrated on high frequencies. So I have this concentration of the size of the spectral sample. I want to know for what case is this large. If it is the concentration is for very large enough k, then it's more likely to be sensitive to the noise. And quantitative information on this concentration of E of fk is going to give me information on how t will change with n. Okay, this is crude in the sense that all of this are going to be dependent on n. There is an n parameter. So sensitivity will depend on t being a function of n, and where is it concentrated, I have to understand as a function of n. Okay, so this is, yes? So I take every bit, I have n bits. So each bit I decide to resample with this probability. And when I resample, I replace it by a new symmetric bit. Okay? It's just, I'm replacing it by a new bit. But I decide to replace or not with this probability. So some bits will just remain the same, some are replaced by an independent copy. Okay? T is anything positive. We will see that I want to understand as a function of t, as a function of n, how does it affect this kind of expectation. Okay? See, if you didn't change at all, if I didn't resample at all, then this is expectation f square, which is just 1. Okay? If I resample everything, it becomes a product. So as t goes from 0 to 1, 0 to infinity, you go from 1 to a product form. And you want to know when does it really have a transition in some form? When does it move away from, when does f of epsilon t go away from f of epsilon? These both are plus minus 1 valued. So it means at some point it has to change from plus 1 to something. to -1. So does it change what is the likely is what you're wanting to understand. And I'm saying that depends heavily on understanding because of this formula. It heavily depends on understanding that which frequency am I putting my mass on, okay? Which frequency is my Fourier spectrum concentrated? If it's concentrated on very, very high K, then smaller the T needs to be for the change to happen, okay? So this is something which will be made more clear later in the continuous context. But as I said, these are just the objects involved in the study, not any explicit result, okay? Okay, so our next shift to things is what is the continuum object I am interested in. I'll only introduce one specific object, okay, of one specific example. There are more examples one can ask, but here's the basic example. Okay. I take a stationary Poisson process in R2 with intensity lambda. It's a collection of points on the plane. What does it mean to say it's a Poisson process? Here is a simple construction, is that I take Poisson points with these many number of Poisson points in a large box, okay, proportional to the volume of the box times a factor lambda. I put these many points uniformly and independently inside a box and let n go to infinity. Then I cover the entire space. Okay, there are various ways to describe a Poisson process. One easy one I find is to say this. On very large scales, I'm just going to keep on putting Poisson points on larger and larger boxes, more and more, and let the box size go to infinity. Okay. So it's an analog. If you want to put, instead of putting n uniform IID points or n to the d uniform IID points, I put a random number of them. Okay. It is because I cannot put IID uniform points on the entire plane, so I have to put it on larger and larger boxes and take the limit. It can be justified, this limit will exist and it will give me a collection of points which does not have any accumulation point almost surely. Okay. So for simplicity, we will be focused only on Poisson points in large and large boxes, the final question. Okay, so for simplicity, you can just take it to be Poisson points on a very large box, put uniformly and independently. And the model of interest, what's a percolation model of interest to me, is that I put balls of radius 1 around each of these points, take their unions. Okay, for example, like this. I just put balls of radius 1 around each of them and take the union. And question in percolation is, does this have a unbounded component? You know, there are many components here. As you can see, the balls form connected components. Question of percolation is, when is there an unbounded component? Depending on lambda. As I make lambda larger, there are more and more points. So there is more and more likelihood of having an unbounded component. Does it ever happen at all? When does it happen? What can you say about the sizes of the components and geometry and structure? So that's the basic question of percolation. We will take some particular aspect. So this is the occupied component I'll be often talking about. And let's now narrow down the continuum question to what I said about the phase transition. Like I said, what we will look at, is there a left-right crossing of a large box by this occupied component? So I have this union of balls. I want to know from left to right, can I go by the occupied component? In this figure, you can. Okay, this is an example of a crossing. And for just convenience, I've put some of the figures here also on board. So this is what we call as crossing. For me, it's left to right. Okay. And here is a basic phase transition result, not often the way first result, but this is the result of interest to us. Cross L is the event. I'll also think of it often as an indicator random variable, sometime plus minus 1, sometimes 0, 1. Okay, we will keep alternating between plus minus 1, 0, 1. What is the probability of crossing? It is known that there is some lambda c, which is neither 0 nor infinity, which is strictly between 0 and infinity, such that if lambda is below lambda c, the crossing probability goes to 0 as L goes to infinity. Asymptotics is L goes to infinity. As L goes to infinity, this probability goes to 0. It goes to 1 if lambda is greater than lambda c. It's called supercritical. In between, exactly at lambda c, it's a very complicated result due to Rousseau, Seymour, and Welsh, showing that I should have been a bit careful or put quote unquote, it's not exact convergence. It's a lim-sup, lim-inf result. Okay. This crossing probability, the lim-sup and lim-inf are within some interval A to 1 minus A, where A is something strictly positive. So that is, this probability is bounded away from 0 and away from 1. When lambda is equal to lambda c, this kind of thing is to be interpreted as bounded away from 0 and 1. Above and below, it's a convergence itself. Okay. So this is a phase transition, what is called as a phase transition result. That is, it suddenly goes from 0 to 1, the probability. And there is exactly one point where it's a constant. Okay, it's somewhere in a, I mean, it's not exactly constant, but in an interval away from 0 and 1. It's non-trivial. So there is one non-trivial phase, and then below that it's subcritical and supercritical. Okay. So this is the basic result in continuum percolation now. Proved in many, many models. Now there's a lot of progress. Yes, Shubhajit. The lambda c will change. Yeah, lambda c depends on the radius. So this is now in the plane, it is now even proven you can put random radius. As long as the second moment is finite, this result is true. Balls here is convenient. Yeah, it's the same thing, but I can think of it as a graph, but balls is a little nicer. For example, if you put random balls or random shapes, then there's asymmetry. Okay. So that way, both are valid generalizations. People look at both, and such results are known under, as long as you are dealing with compact shapes, I think the results are okay. Unbounded, you have to start worrying a bit. Okay. Okay. So this is the result. Everything so far, there is no dynamics, noise or anything. And next I'll just motivate why we want to look at noise and try to give a quick overview of the subject before we actually go on to stating results about noise. Okay. So again, this is just I'll say in percolation theory, in continuum, this is one of the first model introduced in 1960s by Gilbert, and since then widely studied, and one of the simplest models because of obvious reasons. Okay, what I'll say is a few things. There's been a lot of progress in percolation theory. Kind of results I said, they are known for many, many models. They are very robust tools and so on. One thing that is less explored is what happens if you allow these points to move or points to die and be reborn. These things are very less explored, especially in continuum. More or less, I'll say a few works, and I can, there may be a couple of papers I may be missing, but in continuum, there is much less, even though it was introduced in 96 by Hegstrom, Perez, and Stife. And the view we will take is we will think of noise is a dynamic run for a very short time interval. I'm going to run a dynamics on my process. That is, I'm going to allow my points to appear and disappear and do it for a very short time interval. This I will think of as a noise. Okay. Equivalent way of, instead of resampling, there's a way you could have done the resampling using exponential clocks. For those who are familiar with some Markov chain theory, it's a matter of just saying that run each of the bits for some exponential time and then resample when the clock ticks. I'll make that noise part more precise. The first people who had to really investigate this more carefully and formalize these definitions were Benjamin Kalai and Schramm. Schramm will keep appearing multiple times. They really used hypercontractivity, and as already I said about inspired by algorithms, they used hypercontractivity and randomized algorithms. They showed noise sensitivity, that it's sensitive to noise in some way. It's a phenomenon of critical. Then it's a very elaborate motivation. They had a lot of reasons to study this model. As a dynamical model, this is quite interesting to know about dynamics, but it had many other applications, one can say. And then, which was very common for a lot of percolation theory, is that people try to use a result done for discrete bits and do the continuum one by discretizing. Even for the Poisson process, you break the space into blocks and then think of it as a discrete, think of it as a discrete model. And later, then Schramm and Stife came up with it's a very, very beautiful, to me, still surprising. They came up a way to control those Fourier coefficients using randomized algorithms. It's like really a half a page proof in a paper of Schramm and Stife. And they control the Fourier coefficients using randomized algorithms. And this helped to give quantitative but not sharp. So all these, what I mean by sharp, noise sensitivity I'll quickly define soon. And then again, Daniel Alberg, one of the pioneers in this, did this by discretization, and this nice result of Schramm and Strife is what triggered our interest, is that we felt that somehow this way of using Fourier coefficients could give something which is purely continuum, not appealing to discretization. Coming up with a really continuum tool is what we tried with Gunter and Giovanni. And then Garbam, Pete, and Schramm really pushed the full spectral sample approach, understanding the frequency of the Fourier spectrum in discrete percolation and so on. And they really managed to come up with very sharp results. And in a very specific case, what's called Voronoi percolation, Vanovel did something, and then Vanovel implemented their approach. And we have been trying to really carry this out in the continuum, not so successfully is what I would say. Okay, we don't obtain full sharpness. So this is a quick overview, and as I said, continuum, I could probably quote a few other papers of continuum dynamics, but that's about it. Okay, so that's been one of the reasons I've been interested in, is look at dynamical models in continuum, and also to come up with purely tools which are very continuum without every time having to discretize, appeal to the bits, random bits, and then going back and forth. Okay, so hopefully some of this will be clearer later. So let me formally define noise sensitivity and including sharp. So again, Ganesha Stuti in this thing, all the time these things will be appearing in the slide, just for I keep forgetting, so recollection. So please, if you don't mind the repetition. So we have a Poisson process. I look at the occupied region, and then I have a eta t I will define, but for purposes, it's t is always time. So my Poisson process varies with time. It means points can be deleted and points can be added in such a way that at every instance of time, it's a Poisson process with the same intensity. It's a stationary dynamic. Okay, I'm running somewhere, I'm adding and deleting points in such a way that it's always a Poisson process. But points are being added and deleted in time. Okay, it's just like in the resampling case, no matter how I resample, at all times it's a sequence of IID symmetric bits, except that they have some memory of the past. So it's the same way here. And noise stable, I will illustrate it only for this specific event, is that I look at the crossing probability at time, small time t, and I'm saying it should not change. Formal definition, of course, I take the soup, I take the limit as it goes to 0 should be 0. But what we are saying is that if I run the dynamic for a very small time, the crossing does not change. Either there is a crossing at time 0 and time t, or there is no crossing at 0 and no crossing at t. These both do not change at all at very small time. Okay, this is the question of noise stability. Noise sensitivity is the other extreme. Give me any time the covariance goes to 0. These are 0, 1 valued indicator random variables. Covariance goes to 0 means the two events become independent. Okay, so it says for any small time, as I let my L go to infinity, the two events crossing on large boxes becomes independent. You run the dynamics, you perturb the model a little bit, it becomes completely independent. As this event alone, not the entire thing has something, but crossing becomes independent. Okay, so this is what is noise sensitivity. But this is just because this is indicator and in this specific case, yeah. In general, not. But so this is a very weak way of formulating it, but yeah. Sharp, I want to say sharp versions. What do I mean by sharp versions? I will define not noise sensitivity sharp, but noise sensitivity sharp is more, I'll say sharp noise unstable. Why to introduce this arbitrary notion? Because that's what we could prove and not more. Okay. So what does it mean to say sharp? Is there is some time AL going to infinity such that if TL is smaller than AL inverse, then it is noise stable. But if TL is larger than AL inverse, there is an exact time scale below which it is noise stable, above which it is not. Okay. So what does it mean to say that? It means that below this time scale, the crossing probabilities have to be the same. Crossing events have to be the same, not the probabilities. But below this time scale, if I run the dynamic for this very short time scale, depending on L, the crossing does not change. If I run it for a little more, there is a positive probability that these two become different. Okay? That crossing may happen at 0, but not at the small. After small perturbation, I may destroy the crossing. Okay? Or I may not have crossing and I may get a crossing. Okay? And if you want to say sharp noise sensitivity, it means that instead of not stable in this part, you have to say sensitive. Okay, that is TL, AL going to infinity, it should become noise sensitive. That is called sharp noise sensitivity. That is below some time scale it is stable, above some time scale it is sensitive. This is a sharp version that we want to know exactly when does this happen. Okay. So this is a question of noise sensitivity and stability, that you perturb the model a little bit, and then I want to know when does it exactly go from being stable to unstable or stable to sensitive. Okay. Let's say what are the predictions here, and then I'll then state the results after a while. The predictions. If it's subcritical, what happens to the crossing probability? The crossing probability goes to 0. So you can actually show trivially it is both sensitive and stable. If a probability goes to 0 or 1, it's a degenerate random variable, degenerate event, it will be both sensitive and stable. Just by quickly, you can see in the definition, if this probability goes to 0 or 1, then both of them are true. Okay. So this is a trivial case that when the probabilities go to 0, both hold, and this is the only case in which it can be true. Okay. So subcritical, supercritical, this is a well settled thing. The complicated part is in the critical regime. One believes it to be sharp noise unstable and sensitive with this time scale AL, which is L square. L square is the volume of the region. Alpha 4L I will now define. Alpha 4L is what is called the 4-arm probability. It's the probability of having 4 alternating arms from a small box to a big box. So I take a small box. I should have 2 occupied components going from the small box to the big box and 2 vacant components in between them. So this is what is called the 4-arm probability. Is I take 2 occupied components from the small box to the big box, and interspersed, these green parts are the 2 vacant components. Okay. Vacant again is the complement of the occupied part. So this is called the 4-arm probability. There are 4 arms from the small box to the big box, alternating meaning occupied, vacant, occupied, vacant. So this is a probability. This will go to 0, but the exact prediction is L square times alpha 4L. Why is this prediction even expected? I'll give a quick intuition. Why does one predict this? So what are called pivotal points for such a crossing? So if I want a crossing, what's a pivotal point? Is I take points, if I remove if with this point there is a crossing, if I remove the point, crossing should be destroyed. I'm going to look for balls which will destroy the crossing if I remove the balls. What are those balls? Those balls should have some structure like this. It means starting from those balls, I should have a left path, a right path, occupied path. And if I remove the ball, I'm having no path, so there should be a top-down vacant path. Okay? So there should be balls which satisfy this there should be boxes which satisfy this event. And there is a region of L square. So roughly there are L square, alpha 4L, many such points which are pivotal to a crossing. And my dynamic should be run for long enough that I touch one of these points. To change the crossing, I have to change one of these pivotal points. Okay, I have to touch one of these boxes, where by putting a ball I can get a crossing. By removing a ball, I lose the crossing. So I have to touch one of these boxes, and the number of such boxes is like L square alpha 4L, and the time it takes for me to touch one of the boxes is this. Okay, so that's the simple heuristic that drives why this should be L square alpha 4L, because these many boxes are important for the crossing, and that much time I need to run. Okay, but of course that the lower bound part can be checked via this heuristic is clean, but the upper bound is harder because the number of pivotal boxes is also changing with time. Okay, the actual pivotal things are changing with time. Okay, maybe let me keep this one moment. And so why do I care about noise instability also? It's a good question about a dynamical model, that if I run the dynamics for a little while, does it really change, the model change? A particular event, if I perturb it a little bit, is it robust? And in fact, I think one of the things in Kalashram and various computer sciences, they asked it even in the context of some US election. I think it was 99 or something. So this is one of the things of perturbing bits, and does it change or not change? And these kind of questions, various systems ask such questions. That's one reason. And in percolation, two things you ask is, I run the dynamic, it's evolving with time. I want to know, do I see infinitely many times crossing happens, then crossing fails? Crossing happens, crossing fails. Is it possible at all? That can I keep alternating in the dynamic between a crossing and a non-crossing? Is this feasible? What one can show is that if your noise unstable, you can be volatile. What I call volatile is oscillating between crossing and non-crossing. In the degenerate situations, there is no volatility. Okay, it's always zero. There will be no fluctuation at all. But as a consequence of noise instability, one can prove volatility. What more, I'll say something what's called the critical window, which is an important quantity about just static percolation. This is nothing dynamic, this is just static result. Remember, here there is a parameter lambda. Cross L, eta is a function of lambda. Okay, there is a lambda everywhere hidden in eta. Eta has a lambda parameter. We said if lambda is smaller, it goes to 0, lambda is larger, it goes to 1. But what I can deduce from noise instability at criticality, lambda equal to lambda c, we are proving, is that I can make lambda also a function of L. Goes to 0 slowly, fast enough. If it goes to 0 slowly, it becomes 0. If it goes to 0 slowly on the higher side, it goes to 1. So I get this very sharp result than even this. I get a sharper result than this. Here lambda is fixed, but here I'm changing the lambda with L. Okay. So this is a finer result than the earlier result, which you get out of proving noise instability. So it's a kind of thing that the dynamical model has an implication for the static model. This is a model with no dynamics. People try to prove such results to understand in sharper forms of the space transition. But if you have a dynamical result, you get it much easily. This is kind of argument due to Benjamin, Kala, and Schramm, which can be repeated verbatim in many, many cases. Okay. Quickly, what are the exact dynamics is a less important, but very important to not so much for the result, but if you are interested in more technical points, this is what is called the birth-death process or Ornstein-Uhlenbeck process associated to a Poisson. What do? Existing points are deleted at a unit rate. Every point has an exponential clock. When the clock ring points is deleted, and you add new points according to an independent Poisson process. So what does it mean? At any time t, I delete points with e to the minus t and delete a point in a new process. Eta prime is an independent Poisson. So you take two Poisson processes, eta and eta prime, which are same, independent. In one of them, you delete with probability e to the minus t. In one of them, you delete with 1 minus e to the minus t, and then superimpose these two. Okay? You delete with e to the minus t in one, you delete with 1 minus e to the minus t in the other, and you superimpose these two together. Okay? And then you can show that the result is a Poisson process. Okay? And that is my eta t in distribution. It's not a dynamical description, but it's a description at any given time t. It has this distribution, which is same as eta. So all of them are Poisson process. Okay. So just the notation, this just means that I'm deleting points, or did I make, okay, retaining points with e to the minus t, but okay, this doesn't matter. I'm having 1 e to the minus t, 1 minus e to the minus t. So I retain points with this, and then in one e to the minus and other 1 minus e to the minus. One can show this is a reversible Markovian dynamics. So it has a stationary with respect to the Poisson measure. And it's not the only dynamics of interest in people study. You can ask, why do I only kill and or do this birth that? You can say retain all the points and keep shifting them. Or whenever you delete a point, you add a new point somewhere else. You can ask any number of dynamics. There's infinitely many possibilities. It's something we would like to investigate. Points can move according to a Brownian motion, die and reallocate. All these are feasible, but in some sense, this is one of the simplest possible dynamics because it has a lot of independence. Points are being killed and born, so they have a lot of independence. So one advantage, if you prove noise stability with respect to this dynamic, you get noise stability with respect to conservative dynamics. Conservative, I mean points are preserved. Number of points is always constant. Okay, I may reallocate them, I may shift them, but the number remains the same. So you will get noise stability with respect to this birth-death dynamics will give you noise stability with respect to conservative. Vice versa, if you prove noise sensitivity with the conservative dynamics, you will get noise sensitivity with the more this birth-death dynamics. So it's really not that this is the only dynamic you should look. It is really nice if one can build a general theory for studying more dynamics, but this is even in discrete setting, it's not so well studied. Okay, so let me, after all the thing, precisely, at least I've, I think, introduced all the objects. So let's state the result. So what do we show in the couple of works? Well, sharp noise unstable at this time scale for this model. So I said the crossing probability result holds true for a wide variety of models. But when I want to prove the sharp noise or dynamical versions, it's known only, like as far as I think, it's only for a couple of models, or maybe some minor variants. So what do we mean? We say that it's noise stable when TLAL goes to 0, that crossing does not change. It's not noise stable if TLAL goes to infinity, about this time scale. And we cannot show, ideally we would expect noise sensitivity here, but what we show is noise sensitivity at a slightly larger time scale. Point is the C is non-quantitative. In the sense we don't have an explicit C here. And definitely C, the methods will not give C equal to 0. It's not a technicality the way we prove this part that we can pull down C all the way to 0. So ideally we would expect C to be 0 in this part. Okay. So this is our result. I'll let it be for a minute before. Any questions? Yeah. So alpha 4 is the probability of having 4 arms from a unit box to a box of size L. Well, not exactly, but there are like bounds of some nature. Okay. So it's a question of interest in general for a static model. You can ask, instead of 4 arms, you can ask any number of arms you want, maybe 10 arms, but huh?
How much smaller is this?
A unit box.
Unit box.
L is going to infinity. Okay. But usually when people prove, they can prove it at all scales. Like L1 and L2, it decays polynomially. There are predictions about the exponents and all that. So the predictions, it should be L to the power minus something. Okay. And what we need is some crude lower bound in the proof, which are known. That is needed, but not the exact exponents. So I think alpha 4 is L to 1 over L to the 2 minus epsilon, if I'm right, for say some epsilon or something predicted. So it cannot be like 1 over, so this will go to infinity. So that already tells you something. But it's a little below, it's above 5/4 or something, stuff like that is known. Okay. But what we need is much weaker lower bound, that it decays polynomially or stuff is okay for us, something. Okay. And this C is much far away from whatever is that prediction. The C will come from some other arm exponent, one arm exponent, and it is known that that will be far from alpha 4L. So that's why I say that this gap cannot be bridged by some limit or something. Okay. Now we will go back. It will seem a repetition of the very first slide on Boolean functions. I'll try to outline how is the general approach to prove something like this. Okay, what is the general way to prove something for models, and try to indicate that what are the challenges and so on. So, without defining the object, I'll say there is something I'm going to define, what's called a spectral point. Given a stationary process, let me take a function which takes in -1. -1 plus 1 is convenient because then the square becomes 1. Okay, that's convenient for some reason. You will see technically. We have a process, it's again a point process, associated to this Poisson process and the functional f. I call it the spectral process, I'm not even defining it. I will say something is the energy is the probability of cardinality is equal to k. This is exactly like in the spectrum of the Fourier analysis of the Boolean functions. I had something of some cardinality of the spectral sample k is what we call the Fourier energy. Okay, we define the spectral sample, so there is an analogous spectral process. And you can forget everything and start with this formula. All we needed in that analysis was an analog of this formula. That if I take a time t and time 0, expected function is a sum of e to the minus kt times the Fourier energy or the spectral energy of level k. So I have exactly the same formula, and then it's simply nothing but the exponential transform of this cardinality of the spectral sample. Okay, so we will keep oscillating between spectral sample, which is the discrete terminology, and spectral point process, which is the continuum. I'm sure even in the paper there may have been some mistakes of this nature. We keep oscillating, and one simple bound for this is the Jensen's gives you a lower bound, and the prediction comes from there. So Jensen's tells you at least if this goes to 0, this will go to 1. And it's a f is a plus minus 1 function. If the product of expectation goes to 1, it means that the function is same at time 0 and time t. So that gives you a simple starting point. Okay, but how do I compute? So now the point is to understand the size of the spectral sample. Okay, it just seems to understand a random variable. Okay, not even the finer properties of gamma f. But somehow it's funny that even to understand this number, I need to understand the distribution of this as a set. Okay, you need more finer properties to understand this. So here is what is called a related process, which I have already informally introduced, what's called the pivotal point process. Is all those points in eta such that if I remove them, my function flips. Either from +1 to -1 or -1 to +1. My function flips if I remove the point. This is exactly what we discussed when we discussed the 4-arm probability. And what we argued is that the expected number of pivotal points for the crossing event is L square alpha 4L. Okay? And then here is a very generic result which says that give me any bounded subset. The expected number of spectral points and the expected number of pivotal points are equal. Okay? So it tells me that these two are actually equal in the first moment. What is not true, which is the big difference between the discrete and continuum. In discrete, even the second moment is equal. In continuum, even the second moment is different. So this is something when we started, we thought, okay, it's going to be analogous. You keep using some orthogonal expansion and series expansion and keep going through. Yes, you get this formula, then you get this. And the next case is even the second moment has to be equal. In discrete, it was proven by Gilles Calais. Not a long proof, it's observation by Gilles Calais. We thought, okay, we will also get it for this case, but it turned out second moment was not equal. Okay. But first moment is equal. And then what does it mean? I know that so I expect, what is my intuition? is that this random variable should be concentrated around its mean. The mean is equal to the mean of the pivotal set, and the pivotal set has L square alpha 4L roughly. So I expect now this set is L square alpha 4L, at least the first moment I'm correct. I see many of the students who did my course in BMAT, they can do the first moment method now and derive the first part. Okay, so for all of them, it's an exercise, and even for others. If it's noise stable at TLAL goes to infinity, this first statement, the lower bound, is just a first moment method. The moment this estimate and this identity is true. And I've already given the argument here. You can immediately plug in and do it. Okay. So this is always the easy part. Okay, I can get the upper tail for gamma for this spectral mass. Okay, I can get the upper tail. The challenge is in the lower tail. That's where these two things come about. Okay. So just this is what we have already proven, or I have sketched a proof, and this is always the easy part. Because okay, the reason is pivotal process. Why do we compare spectral and pivotal? Pivotal is very geometric. Spectral is a very analytical thing. As you see, I have not even given the definition. I'm trying to hide it until the last slide. Okay. Whereas pivotal is something you can define very straightforwardly. It's very geometric. It can be understood much easily. It's like where if I remove a point, whether it changes or not. So it's easy to analyze pivotal, not spectral. And the entire thing is somehow use that information from pivotal to go to spectral. Okay. Okay, next bit. Again, often this formula, what I said, is called Mailer's formula. We have again a Poisson process, spectral, and this energy. We have all these terms. I want to understand EF of K, as we said. I want to understand EF of K. There's a very beautiful result which came up. We generalized the one originally due to Schramm and Steiff. Stopping sets are analogs of randomized algorithms. So I take a subset of R square. I call it a randomized stopping set. It's a random subset. Okay, depending on eta, depends on the Poisson process. And then what do I say is that if you give me a fixed set B, I want to know is my set Z contained inside B. This should be determined by the configuration inside B itself. Think of Z as some kind of algorithm that I'm revealing space little by little. By exploring points in space, I'm revealing it little by little. At some time, I decide to stop. But I should stop only based on what I've seen so far. Okay? I slowly explore space, and at some point I say I'll stop. I won't explore anything more. And I don't look outside what I've explored. I'll give one example for our context later. And then I want a stopping set to determine my function. That is, I look at the configuration inside this random set and I know what's the value of my function. Then what did Schramm and Steiff come up with an inequality, which I'm stating in the continuum context, is the Fourier energy can be controlled K times what is called the revealment probability. What is the revealment probability? It's the supremum over all points. What's the probability? A given point belongs to the random set. So in terms, this is the Schramm-Steiff inequality. Like I said, our exercise is to guess the discrete analog. This is very easy. You can try to guess what will be analog of this in the discrete Boolean function, the original Schramm-Steiff inequality. Okay, so they came up with, this is to me still quite this thing. They control the Fourier coefficients by how good an algorithm you can come up with to explore this function. If you come up with a very smart algorithm that needs only very little of the space and can can tell you the function, then you can control the Fourier energy. Okay? So this is this thing, and what is the consequence is if this, I can make it go to 0 for every L, I find a random subset, explore it, find the function, and if this delta goes to 0, okay, then you can show that this will happen for TL greater than this. So you can plug in, the machinery is very simple. This is the bound delta ZL, plug in here, and then crank up do some analysis, and you can deduce some result of this nature. So what you will get is, it is noise sensitive for TL greater than the square root delta ZL. Okay, what's a stopping set for a crossing? Let's give one example. So I have my crossing and I want to explore this crossing. Okay, I want to somehow come up with a set that some kind of stopping set that will tell me that if I know the thing inside this set, whether I have a crossing or I don't have a crossing, I want it to be very small. What is the way to do it? Here is it. You pick a vertical line. It's a full vertical line. You pick a vertical line at random in the box. Start from this. Look at the occupied component intersecting the vertical line. Explore it to the left and the right. So explore the occupied region intersecting this line to the left and right. If there is a crossing, you will go all the way to the left and right. You know there is a crossing. But if you stop somewhere in between, you know there is no crossing. Okay? And the key trick is to start with a random line. It's very important, you will see. You start with a random line and explore it to the left and right. In the sense you explore based on the occupied region intersecting the line. Now, here is a simple this thing. What is the probability a point belongs to Z? It means there should be an occupied path close to the point starting from L. From this point, I should be able to find an occupied path to L. That's the only way I'll explore this point in my stopping set, because I'm starting at L and exploring only via occupied component. And because the line L is chosen at random with this thing, you can get a 2 over L. You have to integrate over the line L takes values in 0 to L, and then with probability some 1 over L, and a little bit work can show you that this is 2 over L, and there is alpha 1, what is called one arm crossing. There is just one arm from W1 to WS, L to the minus C. It will get some constant. Not the same C, but some C. This is known, but the key point is this is a question of static model. There's no dynamic. Every time you see, I'm replacing the dynamic one by a static. Okay. And what is true is that this polynomial decay is known in many, many models. This is fairly general. Okay. This is very robust tool. This tool is very robust. Okay. But so this proves this last bit. It's very robust, but what misses is the sharpness. So this is where we are at, in the sense that you can prove this lower bound, you can prove a noise sensitive for many models. Both the lower and upper are true in great generality using much. This is simpler. This is with the algorithmic bound. This will work well, but not sharp. And what do we do for in between? I'll not be able to go into the full details. I'll say we try to come up with general criterion. We try to come up with general criterion to ensure this not noise stable bit is true. What are the general criteria we need? There is a lower bound on forearm. So it was asked that how should this be? So this can be, you can already see this is like a 2 minus epsilon, but with an epsilon prefactor. Okay. So I need a very crude lower bound. This was for us luckily proved by Manalasco and Santaro recently. The hardest part of the proof, the challenge was to verify what is called quasi-multiplicativity. This was done by Keston originally in the discrete case. We adapted. Even sketching out adaptation is like 10 pages. But the point here is that to say at two different scales, the forearm probability behaves nearly like a product. Okay, I go from 1 to L and L to some other scale. I should get like a product structure. And then the last two things are somewhat more standard to prove. Okay, so any model that satisfies all these four will exhibit the sharp noise instability. But somehow these first two properties are a little more tricky. And I'll probably in a minute, even though spectral point process is important and it's much a little more technical, and you will see why. I'll but nevertheless quickly run through the definition and leave it for people who are interested to look further. Pivotal point process, as I said, is much simpler. And we know this. And the correlation functions, I'm not going to even say, but these are some kind of derivatives. Okay, these are derivatives. This what is the effect of adding a point at x1? What's the effect of adding a point at x2? These are product of derivatives. Okay, these are to be thought as dx1 is a derivative. It's a product of derivatives. Now, for general Poisson process, we don't need to do the Fourier-Walsh expansion. It was done by it's called the Wiener-Ito chaos expansion, which is again a series expansion. So I'm hiding all the terms here, but all I want to emphasize is there is an expansion, there is a well-studied series expansion called the Wiener-Ito expansion, its IK are some integrals, UK are now known product of derivatives, but iterated derivative. Okay, a minute or two. Yeah, thanks. So these are iterated derivatives, these are product of derivatives. That's the big difference between pivotal and when I come to spectral. Now, it's a series expansion, orthogonality properties and everything is true. The energy is given by expected square of these terms. There's a k-phi. So all I'm trying to, in a quick way say is that you can get analogs of this. These are more analytical and technical things, but nevertheless, you can define this. I can define now a spectral sample. What's the size of a spectral sample? I have these energies in terms of these derivatives, and I will say the most important is the last line. Spectral point process, I can explicitly describe for any given point process, the way to describe a point process, the simplest way is to describe all its correlation functions. Like you give me a random vector, I have to define all the possible correlations. So for a point process, I want to define all the possible correlations. You see, this is a pivotal. It's a product of derivatives. Here, it's the iterated derivative. This is really the kth derivative square. This is the product of derivatives. That's the difference between these two. Why this is easier than this. But nevertheless, we have an explicit formula. And like I said, immediate first correlation functions match up. K equal to 1, both have the same intensity, same correlation functions, so the numbers match up correctly. And you again have to understand the concentration. And what is missing is we analyze the second moment using the second correlation function. And because I have explicit, it's still not bad, get partial concentration results. And again, an exercise that for people who have done the second moment method, you can get a lower bound. If I can control the second moment in terms of some square of the first moment, but it's not so much that straightforward in this. I can only control the second moment of the crossing, not on the full window, but in a smaller window. So there is some scaling properties needed to go between different windows. So it's still a second moment method with some scaling. And I will put the result again. And what I'll say is that not all hope is lost, is that in Voronoi percolation, we obtain sharp noise sensitivity as well. But that's a bit of this thing because the hard work there was done by Hugo Van Ovel, who proved it for a frozen dynamics, which, like I indicated, if you do for a conservative dynamics noise sensitivity, you get noise sensitivity in the more birth and death. Okay. Thanks a lot. I'm sorry for the extra time.
Sir, so for point process for RD and ZD, is that some sort of a Donskoy-like relation connecting the two?
No. What? A Poisson process?
On RD and ZD, assuming that it is there for that too, is that some sort of
No. So on ZD, I think of only plus minus 1. Okay, or just 0, 1 or so. What I can do is say whenever there is a Poisson point in a box,
yes,
in ZD, I call that box to be, I say make it plus 1. Now by the property of the Poisson process, this plus 1s and minus 1s will be independent. Okay, and then I can think of it as some function of independent plus minus 1s, use the discrete tools and study.
yes,
And then make the discretization boxes smaller and smaller. So this is what I said people did sometime. Does that answer your?
Yes, sir.
Okay, thank you.
This gamma f, it's a subset of your point, x1
No.
x2 or not?
PF, good question. PF is a subset of the point, gamma f not.
But then dx1, you have to deletions, right? They are deletions.
But here, this is I'm taking, I can independently define this way. I just take gamma f to be first, I decide how many points gamma f should have. Then I choose these points according to this density. But here I've taken expectation here over eta.
I see. Okay.
So you can ask, can you couple it? But a priori, the definition does not need, it's like in the, the definition does not need me to have gamma f as a subset of the points. Whereas for pivotal points, you are very much right that it's a subset of the points. Okay.
More questions?
So how do we deal with the pivotal point process? Is there some analog of Rousseau's formula or something?
So you do have a pivotal continuum version of Rousseau's formula for these pivotal points. You can have, but then you still, if you want to understand correlations or final structure, because that gives you some coarser information. But what you need to understand is about, how is it that if I tell you there are pivotal points in some region, what about probability of pivotal point and no pivotal point in a nearby or some other regions? So you need these kind of information, for which more is somehow you work sometime with the correlation functions, but as you see, the higher correlations you go, it becomes harder.
More questions? What is this OU process, and so how is it different from the original noise? Like with the intuitively, why this one is better to use than the just the noise?
Well, in some sense, it's exactly what we do with resampling a bit. Is that on every bit you are running an exponential clock, whenever it ticks, you keep resampling it. So here, but I don't have bits, so points die. But when I put it a new point, I cannot put it at that location, right?
Yeah.
So I first decide with something. So it's a complete independent dynamics. It's really very, very, there's a lot of independence. So it's mathematically more easier. But like I said, you may, like even with bits, when you may run a clock, you may say, I may resample a bit. But if I resample one bit and it flips, I may flip some other bit to compensate. I may want to keep the number of plus and minus constant all the time. Okay, so those are more dependent, but whereas the one I said is completely, and this is the, you need some this thing, but it's the right analog in the sense that it happens independently everywhere.
That's like saying that in the bit you have two strings sampled and you decide which one to copy.
Yeah, exactly. The way I could have described that model is that you take two independent strings and then you copy at every stage from one or the other. Yeah. That's exactly this description, indeed.
Any more? Okay, so let's thank